Hi, I'm Brian Prue, tutoring high school physics. Today's topic, springs, energy, and simple harmonic motion. Recall that when you stretch or compress a spring from its equilibrium position, you're going to give it a restoring force. You're also going to give it some potential energy, described by the following equation. Potential energy is equal to 1/2 times k, the spring constant, times x squared, where x is the distance from your equilibrium position. Remember that your spring constant will be different for each spring and will be given to you during the problem. Okay, so when you're diagramming springs, you're going to consider the equilibrium position to be x equals 0. Therefore, you're going to find your maximum potential energy at your maximum x value or your minimum x value. Recall that your minimum x value is going to be negative and refers to a compression. Alright, so let's move on. Let's say that you've got a spring and you've compressed it. Once you let it go, it's suddenly going to expand. But typically, it'll expand out past the equilibrium position. This will give it a restoring force in the other direction, causing it to compress again. And then it'll shoot back, expanding and compressing, compressing over and over again. This is an oscillation, also known as simple harmonic motion. You don't need to know too much more than that definition for now, because we're going to describe it in terms of energy. So once you release a spring, it's going to start moving, and that means it has kinetic energy. This is described by the equation 1/2 mv squared, where m is your mass and v is your velocity. Given this, we can work out the total energy at any time. The maximum potential energy is equivalent to the maximum kinetic energy, is equivalent to the sum of the potential and kinetic energy at any time during a spring's oscillation. So let's work out some problems with this. Let's say that you have some spring with a mass of 5 kilograms attached to its end, and you stretch it out 5 meters. It has a spring constant 5 newtons per meter. What is its total energy? Well, its total energy is going to be equivalent to either the potential energy that is maximum or the kinetic energy that's maximum, but we're only given enough variables to solve for the potential energy. That's okay, let's just do that. Our potential energy max is equivalent to 1/2 times the spring constant 5 newtons per meter times the distance 5 meters squared. So that's 1/2 times 5 newtons per meter times 25 meters squared equals 1/2 times 125 newton meters, and that's going to be 62.5 newton meters or joules. Okay, so now we have the total energy that's going to be in the system. There's also the maximum potential energy. Well, what's the maximum velocity then? Well, we're going to need to use the kinetic energy to work this one out. Recall that the maximum velocity happens at the maximum kinetic energy. So we have our maximum potential energy, that's the same as our maximum kinetic energy. So we can substitute that in for kinetic energy. 62.5 joules equals 1/2 times our mass of 5 kilograms times our velocity squared. Let's multiply both sides by 2 to get rid of the 1/2. That gives us 125 joules equivalent to 5 kilograms times velocity squared. Divide both sides by 5 kilograms. It gives us 25 meters squared per second squared if we go through all the units. Equals velocity squared, square root both sides, and you get a velocity of 5 meters per second. So that's our maximum velocity. Final question. What's the kinetic energy of our particular spring when it's 4 meters from its equilibrium position? Well, now we're going to have to use this one, where the potential energy at any time plus the kinetic energy at any time is going to equal both the potential energy max and the K max. So we've already calculated our potential energy max. Now we just need one of these two to find the kinetic energy. We have enough variables to calculate the potential energy at that point, so let's get going. Our potential energy at that point is equivalent to 1/2 times our spring constant. This doesn't change. But now we're only 4 meters away from our particular equilibrium point. So that's 4 meters squared. We start going through. We get 1/2 times 80 newton meters if you do multiply that all out. So that's going to be equal to 40 joules. Now we just need to plug it in here. We have our maximum potential energy at 62.5 joules equals our potential energy at this point of 40 joules plus K minus 40 from both sides, and we get that our kinetic energy at that point is 22.5 joules. To recap, if you compress or expand a spring from its equilibrium point, you're going to give it a potential energy described by the equation 1/2 times the spring constant times the distance squared. When you're drawing out springs, you're going to set the equilibrium position at x equals 0. You're therefore going to find the maximum potential energy at the maximum x value and the minimum x value. Recall the minimum x value refers to a compression and will be negative. Once you let a spring go, it'll start oscillating back and forth. This is known as simple harmonic motion. Because it's moving, it'll have a kinetic energy equal to 1/2 times the mass times velocity squared. Given this, you can find that the maximum potential energy of an oscillating spring is equivalent to the maximum kinetic energy of that same spring, is equivalent to the sum of potential and kinetic energy of the spring at any point. Alright, that's all for now. Again, I'm Brian Prue. See you next time.